In the previous segment, we concluded that quantum particles can carry an intrinsic angular momentum known as spin, which corresponds to the value L equals to 1/2. As it happens, we can formulate the quantum mechanics of the spin when we start from orbital angular momentum and then adapt our four main postulates to this specific case. This would be pretty much impossible when we would start from the spherical harmonics. For half-integer values of L, they do not make much physical sense. But by proceeding algebraically, it is really quite straightforward. At least in hindsight, most of this was pioneered by Wolfgang Pauli. So our starting point is to try and make sense of angular momentum with L equals to 1/2. Let us list what we know about orbital angular momentum, at least algebraically. So we have three operators that we can view as the components of a vector, and they obey the specified commutation relations. Also, we have the total angular momentum operator L squared, which commutes with all three components. And we have the joint eigenstates of Lz and L squared, enumerated by the quantum numbers L and M, which determine the discrete eigenvalues. Now, if we fix the total angular momentum, hence L, and look at the components with different values of M, then we can group them into a vector with two L plus 1 components. That's really just an ordinary vector with complex components. And if you now work out what the angular momentum operators do to these vectors, you find that they act as 2L plus 1 times 2L plus 1 dimensional square matrices. You can actually determine the matrix elements algebraically from the commutation relations or from looking at how they transform the spherical harmonics if you really want to do this. Just as an example, I here give the expressions for L equal to 1, where you find three really quite simple 3×3 matrices. You can actually check that these have the correct commutator just by matrix multiplication. The sum of their squares, what should be the total angular momentum, is proportional to the identity matrix, which indeed commutes with any other matrix. So this really serves as a number, and the value in front, 2h bar squared, is really just L times L plus 1h bar squared for L equals to 1. For other values of L, you get similarly explicit expressions for matrices of different dimensions. That's all already interesting in itself. As promised, we can do all calculations algebraically. But even more, there is really nothing that prevents us to try and see if we can make this work with vectors and matrices of even dimensions. And the simplest case would then be L equals to 1/2, where we just have two dimensions. So let us develop this, where we simply follow our four main postulates. To start with, we have two states with fixed L equals to 1/2 and M running from -1/2 in integer steps to +1/2. A single step gets us all the way. We call these states spin up and spin down and denote them by arrows. The idea is that this is indicating the alignment of the spin with the z-axis. A general state is then a superposition of these with two expansion coefficients psi up and psi down that we can group into a two-component vector. As always, these components can be complex. The scalar product is then really defined as the complex version of the dot product that I mentioned when we developed the general mathematical language. And we can write the dual state either in Dirac notation or as a complex conjugated row vector, so really the Hermitian conjugate of the corresponding column vector. Now, as for our observables, we denote them by S, not L, to emphasize that this is an intrinsic feature of our quantum system, independent of its orbital motion. We need 3 2x2 matrices, one each for the 3 different components. As that is easy, spin up and spin down need to be its eigenstates. So this turns out to be a diagonal matrix, and the diagonal elements must be the corresponding eigenvalues, which are plus or minus h bar over 2. The other 2 matrices are fixed by the commutators, but not completely. There's a little bit of a choice, but that's removed when we say that Sx should have non-negative matrix elements, as we saw for the corresponding 3x3 matrix for orbital angular momentum with L equal to 1. This determines the form that I give here, and Sy then also follows as given. This is really the standard choice for these matrices, and this choice goes all the way back. The 2x2 matrices that appear here without the factor h bar over 2 are known as the Pauli matrices. All 3 matrices as x, y, and z are Hermitian, so they qualify as observables. We can also check that the commutators indeed again work out, again simply by matrix multiplication. Also, the operator for the total spin just works out fine. 3 over 4 is just 1/2 times 3/2, so L times L plus 1 for L equal to 1/2. You can also translate these operators into Dirac notation, even though this is now a case where working with the matrices is typically much simpler. In the third postulate for the dynamics, the Hamiltonian could be any Hermitian 2x2 matrix. We can parameterize this, for instance, by 4 real parameters, little h, with indices as given, which we write in front of the identity matrix and the Pauli matrices. When we discuss quantum dynamics in the next chapter, we will often do this for a spin, because this is really just the very simplest quantum system for which we can study this. How simple all of this is further emphasized when we now look at measurements. When we measure Sz, we can observe the eigenvalues h bar over 2 and minus h bar over 2, so there are only 2 possible outcomes. We again say that we found the spin to be up or down. And the corresponding probabilities are just the absolute value squared of the 2 components of the quantum state, psi up and psi down. So for normalization, these add up to 1, which is really just the length of this vector. Now, Sx also has 2 eigenvalues, and they again turn out to be plus or minus h bar over 2, just with different eigenstates. Using our general definition of the probabilities with the scalar product between the eigenstate and the quantum state of the system, we then find explicit expressions for the corresponding probabilities. Note that this involves the same information as we needed to obtain the probabilities for Sz, just in different combinations. That's analogous of how the position wave function was all we needed to calculate the probability density for momentum. Finally, we also find the same eigenvalues for Sy with yet another pair of eigenstates, now with an imaginary component, and these give us the probabilities as stated. Note the change of sign indicated in blue, which traces back to the complex conjugation in the scalar product, where it affects the imaginary component of the eigenstate. Finally, we can work out some general compact expressions for the corresponding expectation values. For the z component, that's quite easy to remember, but for Sx and Sy, I would probably start just from the shortcut, where you multiply the 2 by 2 matrix from the left and the right by a row and a column vector. Finally, let me mention one nice property of these expectation values, namely when you group them into a vector and take out the factor h bar over 2, this turns out to be a unit vector. We call this the polarization vector, and the unit sphere it sits on we call the Bloch sphere. So you can think of this as a representation of the spin in the three-dimensional world that we are familiar with, where it indicates the average direction into which it points. But note that this is really only on average. We can never know more than one component of the spin at any point of time, and generally find random outcomes for all of them when we do measurements. Nonetheless, the Bloch sphere representation is very useful, and it is often employed for the visualization of states both in quantum optics as well as in quantum computing, which are other settings where one frequently studies quantum systems with only two levels. The quantum mechanical description of these systems is then just the same as we developed here for spin, and in the context of quantum computing, this would represent a quantum bit or a qubit. This concludes our discussion of these general and universal aspects of three-dimensional quantum systems. Now we move on to a concrete example, namely the hydrogen atom.